Hi, Assalamualaikum warahmatullahi wabarakatuh. In this video, I'm going to talk about the scenario of having more than two independent samples. For example, you might have three different groups, different independent samples, or four, and so on. And in most cases, the general interest is to test the null hypothesis that all these samples here, several samples, have been drawn from the same population, or we are interested to see or to test the null hypothesis that populations here have equal location parameters. And the usual parametric procedure for this objective, for this testing the null hypothesis, is one-way ANOVA, analysis of variance, or F-test. And in order to employ this particular test, several assumptions need to be fulfilled. For example, normally distributed populations with equal variances. So that is the parametric procedure for testing such null hypothesis given here. Now we have the non-parametric counterpart here, and this is what the video is all about. The non-parametric approach, which is known as Kruskal-Wallis test. And note that if you try to employ this test when you only have two samples, then this particular method or test here will be equivalent to the Mann-Whitney test, which you have already seen in chapter 3. So let's move on to the assumptions needed in order to apply this method. So first of all is data consists of k random samples or k random groups. So we have group 1, group 2 until group k, and each group here has its own sample size. The number of sample size in each group here can be similar or can be different, it doesn't matter. Observations are independent within and between samples. The measurement scale is at least ordinal, so it can be ordinal, it can be interval, it can be ratio. And here distributions have similar shapes, and this is particularly important if you are interested to draw inferences about the medians. So in general, when should this method be employed? First of all is when you have ordinal data, definitely you go for this approach. Or if you have data that is interval in, the measurement is interval or ratio, and then it follows a non-normal distribution with small sample size, then instead of using F-test, you can resort to applying the Kruskal-Wallis test. Or you can also apply this particular statistical method when you consider that median is more relevant than the mean. Well, next, what the test does really. Basically, what is the procedure done by Kruskal-Wallis test. Now, the test here first will rank all the sample data from low to high, and then it will consider averaging the ranks for all groups. So imagine you have group 1, group 2, and group K, for example. So it will consider finding the average of each rank. So here the process is going to be as such, and you will see that if the result is statistically significant, that means there is a difference in the groups, so statistically significant different result. That means the average ranks here is not going to be equal, they are going to be of different values. For example, one group might tend to have values that rank higher than the other group. So different average ranks here will indicate differences in the groups. Okay, so that's the idea. In terms of hypothesis writing, we have a general hypothesis and quite a specific one. For general hypothesis, this is how we can write. We can say that for the null hypothesis, the average ranks are all the same. So the keyword here is the same, and you're talking about ranks, okay, average ranks. And the opposite of the null hypothesis, or the complementary of null hypothesis, is the alternative hypothesis, where you can say that at least one average rank is different. So the keyword here is different, over here is the same, okay. Now, if you want to consider specific hypothesis statement, this can only be considered if this assumption holds true, which means distributions have similar shapes. So when distributions have similar shapes, you might be interested to ask or to study about the medians, and this is the hypothesis statements related to the interest. The null hypothesis is the medians are all the same. Again, the null hypothesis, the keyword here is the same, and the alternative hypothesis is at least one median is different. Okay, so that is the keyword associated with the alternative hypothesis. Now, how can you obtain the test statistic? Okay, so first of all is you have to pull all observations from all the sample groups. So what it means really, imagine is if you have data that is displayed like this, group 1, group 2, let's say up to group 3. So we have 3 different sample groups. Well, we can say that probably data, this is all data from group 1. Maybe this is data from group 2. This could be data from group 3, whatever it is. So the first step is to pull all observations from all the sample groups, means you are going to consider all of them, okay, together, and you're going to consider the lowest score gets rank 1. It doesn't matter where it is. So let's say this is the lowest score, so it will be assigned as rank 1. Second lowest gets rank 2. So second lowest could be over here, so it doesn't matter. So this is rank 2. So when you pull all the observations from the sample groups, you don't really care much about the groups here, but you're just considering them all together and rank the observations accordingly, and so on. So this could be the position of 3, this could be the position of 4, this could be the position of 5. So you get the idea. So you will consider again all observations from all the sample groups. When you have ties, when you have similar observation, then you are going to assign those scores with average of the ranks that they would have obtained. Well, let's say that for this one here, this is the similar value to this one. So according to the rank, we already have 1, 2, 3, 4, 5. So this is supposed to be 6 and 7. But then for this purple position here, data set, we are going to assign the rank as average of the ranks that they would have obtained. That means 6 plus 7 over 2, 13 over 2, which is 6.5. So over here is the rank should be 6.5, and over here is also 6.5. And then for the next observation, we move on to, let's say this is number 8. So because originally this is 6, this is 7, but they get the rank of 6.5, 6.5. So the next observation will be at rank 8. So I hope that is quite clear to you all. Now, once the ranking process is done, what you need to do is you need to go on and find the sum of ranks in each group. So look at this particular group, you go on and find what is the sum of it. So this is R1. Okay, find R1, the sum of ranks in group 1. R1, so go on to this second group, sum all the ranks that you have obtained for the second group, so get the sum of it for R2. And similarly, the process is done for the last group. Get all the ranks here, so all the ranks that you have assigned, sum them up, so you will get sum. So this is R3. So basically R3 here is the sum of ranks in group I. Don't worry too much about the process here. If you haven't understood the exact steps given here, don't worry too much, because in the next video I'm going to give a practical example for us to try and understand how the process here is applied. Okay, now once you have done all the steps here, the test statistic can be obtained by considering this formula given here. You can see that in this formula here, n here is the total sample size, which means the sum of sample size in group 1, in group 2, and in the last group, group K. So that is n. N is the total sample size. What else is given here? So ni here is respectively for group, how many groups we have. We have from group 1 to group K, we have K groups. So n1, n2, nk is the sample size in each group, and ri here is r1, r2, rk refers to the sum of ranks in each group. Okay, so that's it. Those are the two things that we need to know. We need to know what is n in the formula given here. We need to know what is ri, which is already explained in step 2. And ni is just the sample size for each independent groups. Okay, next. How to decide whether the null hypothesis should be rejected or not. You will have to refer to the table of chi-square distribution. This is because when you have large sample size for each particular group, large means usually greater than 5, and you will also have like large value of k. That means the number of groups are also large. Well, more than 3 is considered large or equal to 3. And so the test statistic H is distributed approximately as a chi-square with k minus 1 degrees of freedom. So in order to use this particular table here, you need to know what is the degrees of freedom. Degrees of freedom is k minus 1. K here is the number of groups minus 1. So based on that information, you can look at the chi-square distribution table, for example this one, and check the degrees of freedom on this part, and accordingly you will see that if you are interested in 5% significance level, so here is 0.05. If let's say degrees of freedom is 1, then this is the critical value. So 3.841 is the critical value. Well, the decision is you will reject H null at significance level alpha if the test statistic, your H here, is greater than the critical value given in the table. So this is the critical value. Again, don't worry too much if you're not able to grasp the idea or the distribution table or whatever here, because we will look at the practical example in the next video, and you'll be able to hopefully put all the things that I've said together. Okay, now let's say you have ties and there are a substantial number of ties. Therefore, the test statistic may need to be adjusted by considering the adjustment factor. So what is the adjustment factor? The adjustment factor is given by this part over here, sorry. So this is the adjustment factor. So basically, what you need to do is, remember you have calculated H. H is the original test statistic. And then you consider the adjustment factor. So H divided with this item, you will get the new test statistic. So I'm going to call this the adjusted test statistic. Okay, so this is the new test statistic that you can consider when you have substantial number of ties. Some people say, you know, when you have more than 25% observations, more than 25% or more than 1/4 of observations with ties, then you can apply this new test statistic here. You need to do some bit of adjustment. You will see that in doing this adjustment, Let's say you get the value of h um, as something, so h equals to some value. You will see that the adjusted one, the value of adjusted is usually greater than h, because in this process, whenever you get the adjusted test statistic, this process here somehow inflate the value of test statistic, so you will often or always get the value of adjusted greater than the how I say original test statistic, okay, without adjustment. So this one is without adjustment. Now what is t? So t, big T here is equal to t cube minus t, and what is small t here is just the number of tight observations in a group of tight scores. Again, this idea has already been mentioned in the earlier part, earlier video related to non-parametric procedure, but again, don't worry too much about it. We are going to look at a specific example dealing with ties, and you will be able to understand how this process here is employed. Okay, I think that's all for now. Thank you very much for watching, and I'll see you in the next video.